So here's Growlithe. Growlithe is a fire-type Pokemon, and being a fire-type Pokemon, Growlithe likes to sit on this heating pad to keep himself nice and warm. And Growlithe likes to have this heating pad be as warm as possible. So Growlithe basically wants to know, hey, what temperature can I keep the surface of this heating pad at? But we know that this heating pad is filled with electric heaters, and the very core of the heating pad is going to be a bit warmer than the surface. So what does Growlithe want to know? Growlithe basically wants to know, hey, if the core of the heating pad has some safe internal limit that it can't get above, how warm can the surface of the heating pad be? Or basically, what temperature do I need to keep the surface of the heating pad at in order to have the very core of it not melt down to too much fire damage? So let's get started with this problem. So before we get too far, this type of problem isn't just Growlithes and heating blankets, but it's actually a problem that shows up a lot in chemical engineering. So imagine I had a big slab of material, and within this slab I had some chemical reaction. Right, so maybe this is like, have you ever had those like heating things that are sort of like, it's like a little bag, and you shake it up, and then like it gets really hot, and you can warm your hands with it. Maybe this is something like that, right? There's basically some physical volume of material where there's some heat generation going on inside. Some heat being generated within the volume of the material. And maybe it's due, if we look at the electric blanket that Growlithe likes, maybe it's from electrical energy becoming heat. If this is, for example, like a polymer that's curing, oftentimes those processes are exothermic, right? So if we have some material, bone cement, the curing of bone cement is actually exothermic, and sometimes, under some circumstances, can generate so much heat that it can damage the adjacent bone. So we can have heat generated within a volume. Maybe it's some chem reaction that goes to heat. So regardless of what it is, we might have circumstances where we have some slab of material, and that slab of material is generating heat. And so what might we do to try to analyze this system? Well, if we have some system and we get knowledge about it, we might want to say, hey, as a function of position x within my system, can I derive this temperature profile? And of course, this isn't going to be quite so simple as what we had before, where we just had a hot side and a cold side and conduction going through it. Here we have heat being generated within the volume of the material that we need to consider very strongly. So if we frame this in terms of let's frame the rest of the problem in terms of this chemical reaction heat phenomena, right? So let's say that I have this slab of material, and this reaction is going on inside of it. So heat's being generated within the volume, and there's sort of like a volumetric heat generation. A volumetric heat generation term, which would have units of watts per cubic meter. And let's call this volumetric heat generation Q dot of the reaction. And I know I used little q for heat flux the other day, but I'm sorry, sometimes we run out of convenient letters to call things, so we'll just call this Q dot of the reaction, and this is a volumetric heat generation, as opposed to watts per meter squared heat fluxes that we talked about the other day. So volumetric heat generation is this Q dot for the reaction. Let's say I know some geometry of this material. For example, it has some thickness L, and the surface of the material, basically it's like L thick, but it has some cross-sectional area, let's say AC, throughout, and we have this x right here. So x is sort of this coordinate that goes on here. Let's say we know the material properties of this. We know its thermal conductivity K as well. So we have this heat being generated within the volume of this material. It has a thermal conductivity K, a thickness L, a cross-sectional area, and we want to derive what the temperature is as a function of x. And why might we care about what this temperature as a function of x? Well, we know that we want to know, hey, I might have control over essentially what temperature I keep the very top surface and the very bottom surface at. So I want to know what temperature to keep the surface at, so I don't get meltdown in the middle. So there's some safe limit that this material can, let's say, withstand. Maybe it's melting temperature or something like that. So basically I know in the middle I need to keep temperature less than, let's say, some safe limit. So in the middle I need to keep whatever temperature exists in the middle, I need to keep that below some safe limit. So I want to know, hey, what temperature do I need to keep the edges at in order to have the middle be less than the safe temperature? So I want to know what temperature to keep the surface at. Let's call it T edge. So if I keep the edges at some temperature, the middle is probably going to be a little bit hotter than that due to the volumetric heat generation. So if I need to keep the middle below some safe temperature limit, what temperature do I need to keep the edge at? So that's going to be our problem. But in order to sort of relate temperatures at the edges to temperatures at the middle, I'm going to need to sort of derive this whole temperature as a function of position x within the slab in order to do that. So that's where we're headed. So what can we do? Well, this is a problem that if we're looking to derive a profile, we are going to need to employ. So if we're looking to derive a profile, well, when we derived velocity profiles back in the fluids class, we used a shells type strategy to solve this problem. And that's the same process. That's the same type of problem that we're going to do for heat transfer right now. So we're going to use shells to derive this temperature profile. Only instead of using conservation of mass and momentum, in this case, we're going to do it with conservation of energy. So what's our problem-solving strategy? We're going to use shells, because shells basically allowed us to derive profiles. So we're going to use shells to derive T of x with conservation of energy in that shell. And if you look back in your notes to the general steps for shells, we basically, had step 0 was to gather info on the problem, and we kind of have already done that right here. The next step for shells is to define the shell, including choosing our delta dimension. After that, we applied conservation of, well, normally when we used to do shells for velocity profiles, we did conservation of mass and conservation of momentum, but for this type of problem, we're going to do conservation of energy, because that's going to help us get information about temperatures, right? Temperatures and energies are very closely related to one another. And then after that, we can divide by shell volume. And when we divide by shell volume, after that we can take limits as deltas go to 0, and that's going to give us things that look like derivatives. After we do that, we'll end up with a differential equation, and hopefully we'll be able to solve this differential equation. After we solve we'll have a differential equation on hands. We'll integrate to solve our differential equation, and when we integrate, we'll get constants of integration. So we can apply boundary conditions to resolve our unknown constants, and hopefully when we apply our boundary conditions, we can apply our boundary conditions perhaps in terms of edge temperatures. Maybe we can also make some relation to our safe limits, things like that, right? So applying our boundary conditions will basically bring in these parts of the problem that we care about. Then once we get our result, we'll basically do some algebra to manipulate it to get to what we care about. Which is basically what is our safe edge temperature in terms of all of these given parameters that we care about. And then just as a follow-up, just kind of after I'm done talking about all of this stuff, I'll talk about shells in cylindrical and spherical coordinates. You know, hey, can we develop shells not just in a sort of rectangular geometry like this, but also in cylindrical and spherical coordinates? So let's do that. All right, so we've gathered our info. Now we're going to define our shell. So when we define the shell, we want to choose. When we were doing fluids, we oftentimes chose 2 delta dimensions. Spoiler alert, for heat transfer, we're probably only going to really need to choose 1 delta dimension, and the delta dimension that we choose is the coordinate where we expect variation in temperature. Right, so what do I mean here? Well, I anticipate temperature varying with x. I anticipate the core of this material to be hot, but the edges to be cooler, as heat is generated within the volume and then is conducted through the material towards the outside. So I anticipate temperature varying with x. If the slab is large, which I guess is something that we could assume, if the slab is large, then I don't really anticipate too much heat kind of flowing out of the sides as compared to flowing the shorter distance to the edge right here. So what's the key thing here? We're basically going to choose delta x as our delta dimension. So what is our control volume going to look like? Well, I'll sort of draw it right here. Just imagine this is kind of the top plate, or this is the top surface. Choosing delta x as a delta dimension is basically saying, hey, our control volume is kind of one slice of this material right here. So if I sort of took this material and kind of sliced it up into a bunch of slices, each slice having a thickness delta x, what would that look like? This is what it would look like. So what does my shell look like? My shell has a thickness, let's say delta x. The position at this point in the shell is at location x, and the position at this top point in the shell is at location x plus delta x. So that's what's going on with the shell. And if I want to sort of square away the other dimensions of this shell, well, we weren't exactly given a length and a width, but we know that this surface, both on the top and bottom, has a cross-sectional area, AC. So here's our shell right here. All right, so Growlithe is a very patient Pokemon, and Growlithe is willing to wait enough time for this system to be in steady state. So let's start squaring away some of our assumptions. So we're going to assume that we're in steady state. We're going to assume that we only really have temperature varying in x. So we're going to assume t is a function of x only, and that consequence of t being a function of x only is that we don't have heat flow in y or C. So we essentially only have temperature variation and only have heat flows in the x direction. So that's basically kind of what we're assuming right here. So with these assumptions in place, we can now proceed with thinking about conservation of energy for the system. So I could plop down that whole big long version of conservation of energy that we talked about in the previous lecture, or I could sort of start with a slightly more abbreviated version of it right here. I'm going to do the abbreviated version today. So we could basically have our accumulation term is equal to our ins minus our outs plus any generation that we have within our system. So, that big long conservation of energy that I had essentially boils down to these four terms right here. So let's sort of think about what these four terms are right here, and sort of do so in the context of the volume that we've defined right here. So if I think about accumulation, well, actually, because we were assuming that we're at steady state right here, we have 0 for this term right here. If I think about what's going on with this shell, we said, hey, we have heat being generated, within this volume, and that heat eventually gets conducted out to the side, gets conducted out of the side. So some of that heat leaves the top and some of that heat leaves the bottom via conduction. Heat is being conducted continuously throughout this material. But if I'm thinking about, hey, I want to formulate these conduction things, I'm going to be talking about QX's, right? Heat flows in the x direction. And if I think about heat flows in the x direction, these heat flows, this Q sub x is basically defined to kind of be in the positive direction. So if I think about ins, I have some heat flowing into the bottom surface right here, and I might call this QX, where this x indicates that it's in the x direction, and I might evaluate it, but I might evaluate this heat flow at x. So my in is basically going to be QX because it's in the x direction, and evaluate it at position x because it's sort of heat flowing into this bottom face here. Similarly, I have some heat flowing out at the top right here. So take a moment now, pause and ponder. Is this heat flowing out the same? Is this heat flowing out the same as this heat flowing in? Well, actually, no, they can't be the same. Why can't they be the same? Well, I know I have heat being generated within the volume of this shell right here. And, if there's no accumulation and I have some generation, I have some heat going in, some additional heat is generated, I must have more heat flowing out than was flowing in if some heat was being generated in this system as well. So what does that mean? I need to call this heat flow out something different. Let's call it Q sub x, but it's evaluated at x plus delta x, and these two Q's are not necessarily the same as one another. So what might that look like? I could call it Q sub x evaluated at x plus delta x. So there I have it. And then finally, I could have my generation term. So this generation term is basically the heat that's being generated within this shell. So take a moment now, pause and ponder. What is this heat generation term? What is this heat generation term in terms of some known or given constants, or some information about this? So what's this heat generation term? What's the heat being generated in this shell in terms of some information that I've defined here? Well, all of these terms, this accumulation, ins, outs, and generation, they all need to have units of watts, right? These all have units of watts. So my generation term also needs to have units of watts. If I think about it, this whole slab had some volumetric heat generation, Q dot of my reaction, watts per meter cubed. So if I multiply this Q dot reaction times the volume of this shell, then that's going to give me the heat, the watts being generated within this slice of the material. So what's the volume of the shell? Well, the volume of the shell is the cross-sectional area times the thickness. So it'd be like AC times delta X. Right, so that's the volume of my shell. And if I multiply the volume of my shell times this volumetric heat generation, watts per meter cubed, then I'm going to have something that has units of watts. So I'll call it my Q dot reaction right here. So here's what I have it. So I would say now I've successfully applied conservation of energy. What's the next step? Take this equation, divide by shell volume, and take limits. So I have this equation here. I can divide by shell volume and do a little rearranging. When I do that, I end up with 0 is equal to minus qx evaluated at x plus delta x minus qx evaluated at x divided by delta x. I divided by shell volume, so I have a 1 over AC, multiplying this as well. And then on the right, I divided by shell volume, so all I have left in this second term is Q dot of my reaction. All right, so then I have this thing right here. I can take limits. And so what am I left with? So I'm left with minus, I guess I'll have my 1 over AC, and this would be dqx dx plus my Q dot of my reaction as well. So I have a differential equation. We assumed that temperature is a function of x only, and if temperature is a function of x only, then it would be also true that my heat flows are a function of x only as well. So if my heat flows are a function of x only as well, these partial derivatives can become ordinary. So here I have it, minus 1 over cross-sectional area dqx dx plus my Q dot of my reaction. Okay, great. So what have I done? Well, we divided by shell volume, we took our limits, and we got ourselves a differential equation. Unfortunately, what we were hoping for was a differential equation where we had temperature as a function of x, but here we had on our hands, here we have on our hands a differential equation instead for heat flow. Bummer. So take a moment now, pause and ponder. Is there a way to, maybe it's not exactly related to this, but is there a way to get this, to start putting this in terms of temperature or something related to temperature? So pause and ponder. Is there some relationship between temperature and, let's say, heat flow? Why, yes, there is. This heat flow is a heat flow due to conduction, right? So this is something due to conduction. So this heat flow is also governed by Fourier's law. So we'll take a little sidebar over here. So our Qx is defined, occurs due to conduction, which means it obeys Fourier's law. So what is Fourier's law? It's Qx is equal to, and if we put it in terms of heat flows, it would be Qx is equal to minus K times cross-sectional area times dt dx. And we can use ordinary derivatives here because temperature is only a function of x. So what does this mean? We can now take Fourier's law, right? The Qx obeys this So we can take this and we can plug it in all the way down here. So what does that look like? We have 0 equals minus 1 over AC d dx of q of x, which we can plug in this thing here, minus k times AC times dt dx. And then we still have our plus q dot reaction going on right here. So, what does this look like? Well, this is a differential equation. It's kind of a nasty one. We might need to do a little bit of work on it in order to resolve it, but hopefully this is one that we can solve. So, what did we need to do? Well, so we had this right here, but we needed to, we couldn't just get our differential equation. I should add a little note here that I had to first apply Fourier's law in order to put this differential equation not in terms of heat flows, but rather in terms of temperature. So we did that right here. Let's see if we can make some progress on this differential equation right here. So here I have my differential equation. Well, if I notice k and AC are constants with respect to x, so they can be pulled out of this integral right here. So what am I left with? I'm left with 0 is equal to k times AC over AC. And if I pull these out, then I have a derivative of temperature. So I'm left with a second derivative of temperature. And I have my plus q dot reaction. Of course, these ACs basically cancel out. So what am I left with? Well, I can kind of start bringing stuff to one side and the other. So I'm left with d squared t dx is equal to minus q dot of my reaction over k. Oh, sorry, dx squared, second derivative. So what can I do? Well, I can take this differential equation and I can integrate. I can integrate with respect to x. So when I integrate once with respect to x, when I integrate the second derivative, I get the first derivative. When I integrate the right-hand side, well, these are just constants with respect to x. So I'm left with minus q dot of my reaction over k times x plus, and when I integrate, I'm going to do indefinite integrals, and I was integrating ordinary derivatives. So when I integrate indefinite integrals of ordinary derivatives, then I get a plus c. And spoiler alert, we're going to integrate this again and get another c when we do that. So to distinguish this c from the upcoming c, I'm going to call this one c1. We can integrate again with respect to x, sort of same business here. So when I integrate dt dx, I'm left with just t. On the right-hand side, when I integrate, or on the left-hand side, when I integrate the right-hand side, I get minus q dot of my reaction over k times 1/2 x squared, plus when I integrate c1 with respect to x, I get c1 times x. And then, I did another indefinite integral, so I get another, as of yet unknown constant of integration. So here I have two constants of integration that I need to resolve. So how do we resolve the C1 and C2? Well, we integrated, to resolve the C1 and C2 that we get from integration, we need to apply boundary conditions to resolve our unknown constants. So what boundary conditions do we have? Well, we have two unknown constants, so we're going to need two boundary conditions that relate to this system. Well, I could say, hey, at t equals 0, x equals 0 started on one side of the plate. At x equals 0, I have t edge, and at x equals L, I also have t edge. I'm basically prescribing t edge to be on both the top face and the bottom face of this block. So at x equals 0, t is equal to t edge. also at x equals L, t is also equal to t is also equal to t edge. So what might that look like? I can sort of to plug it in right here. So t edge is equal to, so let's do this first one first. T edge is equal to, I can plug in 0, 0. So it's 0, 0, x equals 0, x equals 0, plus C2. Oh, great. So we can see pretty readily that T edge is going to be equal to C2. So I could basically just plug that right in. I can now take my second boundary condition, and I can say, hey, T edge is going to be equal to minus q dot reaction over k times 1/2 L squared plus my as of yet unknown C1 times L plus T edge. Well, conveniently, the T edge can cancel out from both sides, and this can give me C1 in terms of some known constants. So when I resolve that, my C1 ends up being the following. It ends up being q dot of my reaction over k times 1/2 L. So we can see, if T edge cancels out on both sides, and I can bring this to one side and then divide both sides by L, then I get C1. Then I get this C1 right here. I can now take my known C2 and my known C1, and I can plug them back into this equation here. And what do I get? I get minus q dot reaction over k times 1/2 x squared plus, I now have my known C1, q dot reaction over k times 1/2 L x plus, and my C2 is T edge. So I basically now have temperature as a function of x as well as my edge temperature. So this is great. But what was our goal? Well, our goal was to basically say, hey, at the middle, in the very middle of this slab, where we anticipate the max temperature occurring, at the very middle of the slab, we want to keep the middle of the slab below some safe limit. So we basically want to say, hey, what temperatures do we need to keep the edge of the slab at in order to keep the middle below some safe limit so the heating pad doesn't melt down and Growlithe get very upset? So what temperatures do we need to keep the edge at? Well, we can basically say, hey, we now have our t as a function of x, so we can evaluate this expression also at the middle right here. And we can say, hey, at the middle, we're going to set it equal to the safe limit, and then get t edge in terms of the safe limit as well as the rest of the unknown constants here. So what's the plan? We're going to eval t of x at x equals the center, which would be L over 2. Right, so we're going to evaluate t of x at x equals L, and we're going to set it equal to the safe limit that any point in our heat generator can be at. So what does that look like? Well, we can plug it in. We can basically say, hey, T safe must then be equal to the following. Minus q dot of the reaction over k times 1/2 times L over 2 squared plus q dot of my reaction divided by k times 1/2 L times L over 2 plus T edge. Oops, sorry, T edge should be in red. These are as of yet unknown. And then we can solve T edge in terms of this other stuff, because we're setting this result equal to T safe. So T edge then is equal to T safe minus Q dot reaction over K times 1/8 L squared. Great, we have some result. Let's now, so we did our algebra to get to our result. Let's now take a little bit of a closer look at this result and kind of manipulate some, sort of look at how it factors in. So one of the first things we want to do is check units, right? So this is good. This should have units of Kelvin. This should have units of Kelvin as well. And if we look at this Q dot reaction we said had units of watts per meter cubed. K has units of watts per meter Kelvin, and L squared has units of meters squared. And if you look at and if you do it all out, you'll notice that yes, the watts and watts cancel, the meters cubed, meters squared, and 1 over meters cancel. We have 1 over K, which would have K, so we're okay in terms of our units. A next thing to do is a sanity check. So what does this mean? Basically, our edge, whatever temperature we want to keep the edge, at, has to be a little bit less than T safe, right? So if I have my safe limit, I need to subtract off a little bit from my safe limit in order to have my safe edge temperature. Basically, the edges have got to be cooler than the safe limit, because if the edges aren't cooler, then I'm not going to have that temperature gradient to drive conduction from the center towards the outside. And the higher this, this heat generation term, the more I'm going to have to suppress that edge temperature in order to get all that heat out. But if my thermal conductivity of my material is higher, then my edge temperature can be closer to that safe limit without too much problem. But if the device is a lot thicker, if L doubles, then I'm actually going to need to have a much lower edge temperature, because that heat is going to have to be conducted through a much greater distance before it gets to the edge. So I'm going to need to keep that edge colder in order to maintain all of that heat flowing out of the material to keep the center below the safe limit. So, so this is the result that we have. Great. So let's just take, so I'd say, now we've basically concluded our shells example problem. I'm just going to tack on a quick discussion about what shells might look like in cylindrical and spherical coordinates. So let's say instead of having heat being generated and conducted out of this slab, let's say I had heat generated in a cylinder and conducted radially outwards of it. Do we have examples like this in bioengineering? Yeah, my arm. My arm has muscles in it. Those muscles are metabolizing. That heat gets generated within the flesh of my arm and gets conducted through my arm and out to my skin, where it eventually, exits into the environment, right? So this occurs all the time in bioengineering. It also occurs, I don't know if people have watched Chernobyl, right? But it also occurs in the uranium, the spent fuel rods, or the uranium fuel rods in a nuclear reactor. We basically have nuclear reactions occurring inside these rods, and that heat better make it out. It's got to get conducted radially out as it's being generated within the volume of the material. Otherwise the fuel rod will melt or something like that. Bad news bears, right? So we care about this, in nuclear engineering, but also in bioengineering as well. So so how might we formulate a shell? So we might care about temperature as a function of R in this sort of cylindrical geometry. What's that going to look like? So how might we formulate a shell in a cylindrical coordinate system? Well, I would have, because temperature varies with R, I would want to define a shell with a delta dimension delta r, right? So basically, because temperature varies with r, I want to choose r as my delta dimension to help deal with it. I might say that there's some heat that flows into the inner surface and out of the outer surface. I might say the inner surface is at a position r, whereas the outer surface is at a position r plus delta r. Similarly, there's some heat that flows into the inner surface, and I might say this heat that flows into the inner surface would, let's say, be Q in the r direction, evaluated at r, and some heat that flows out of the outer surface, which would be Q in the r direction, but evaluated at r plus delta r. And these two heats might not necessarily be the same as one another if heat is being generated within the volume of this shell right here. So, what might be some details of the shell? Well, you might be given, for example, some information about what the length of the shell is. So, what might be some parameters that you care about? You could basically say, hey, the volume of the shell is going to be delta r times L times 2 pi r, right? Where it's basically, if I took this shell and unwrapped it into a rectangular prism, it would have a thickness delta r, one length L, and then the other length would be the circumference of this right here. And this is, this is basically if I, took delta r to be a thin shell. So this works for the volume, this sort of unwrapping principle. But it's a little bit trickier for cross-sectional areas. It turns out we need to consider two different cross-sectional areas, the cross-sectional area of the inside face and the cross-sectional area of the outside face. So the outer face cross-sectional area is 2 pi times the outer circumference. 2 pi times the outer circumference, which is r plus delta r. And then that whole thing times L, which is basically the area of this outer face right here. We have the area of the inner face, which would just be 2 pi r, which you would get from unwrapping that inner cylinder. And if you have this business here, when we were doing the problem where we had shells and we were deriving the parabolic velocity profile within the shell, we said, hey, we had this situation where we had some quantity evaluated at r plus delta r, and then also an r plus delta r that ended up within it. So, spoiler alert, you might end up with a situation where you have, on your outer surface, you basically have something evaluated at r plus delta r, and then that times r plus delta r as well. So you could sort of keep these two things separate, or you could just kind of combine it wholesale as thing times r, where thing times r is evaluated at r plus delta r, where basically the r plus delta r gets subbed in for both of those things right here, yielding what we have here. So this will make a little more sense when, spoiler alert, you approach a problem where you have heat generation in a cylindrical thing, and that heat gets conducted radially outwards, and you're looking for temperature as a function of r. So there we have it. It turns out you can also do this with spherical coordinates, where you sort of have like a sphere, and you have some r going on the inside and r going on the outside. It's just in this case you basically need to deal with surface areas that are like 4 pi r squared is the surface area of a sphere. But this also works. This whole idea also works for spheres. But I don't think I'll waste everyone's time with going through that. So hopefully this was an interesting and useful lecture in terms of how we can use shells how we can use shells to help us solve problems in heat transfer. So thanks for your attention, and good luck with your study of heat transfer. Take care.